So I'm Martin van Nieuwenhuyzen, Sales Director from Aquatic Control Engineering. And yeah, the presentation is a bit of a snapshot of some nice solutions we put in, particularly from an environmental perspective. There's far more. We've got case studies coming out of our ears. We're quite lucky with that. So if any of these discussions or anything I show in this presentation sparks a bit of interest, come and talk to me, because there's various other things that we've done. Straight away, it's not working. There you go. So yeah, climate change. Everyone knows it's happening, and of course the world is heating up. It's causing more and more storms. The rains are happening all at once, and of course we're having more and more scenarios where we're ending up in floods. That's why we're here, a lot of us anyway. The flooding, it's getting worse year on year. The stats aren't just here for Europe, but also in Asia, Africa, the whole world. We're seeing more flooding happen more frequently. Now, of course, flooding costs the UK a lot of capital. These are 3 different floods that have been taken from 2007 to 2016. It doesn't include the flood that we've just had, which hasn't been costed as yet. These are figures generated by the Environment Agency, and you can see that, yeah, each one of these events has cost over $1 billion, with the 2007 costing $4 billion. You can see that these costs are unsustainable, and also you get nothing in return from it. We spend the money, or at least we go out and try and minimize the damage that's happened, but then the money's gone. And really, we should be looking at building better assets, but trying to make these assets in such a way that they're less damaging for the environment, because, of course, yeah, we can either spend the money up front and keep an asset, or we lose the money because everything gets washed away. The Environment Agency themselves has opened up. I mean, the chairwoman from the Environment Agency has said to maintain our flood defences, we should be spending at least $1 billion per annum. So what do these assets look like? We've got various ones. Some of these ACE are either working on or have delivered. These are non-return valves, for example. So on tidal sites, it lets the water out, doesn't let the water in anymore. We've got land drainage pumping stations. This is at Keadby. ACE are delivering 6 4 cubic metre per second pumps there at the moment. They're being manufactured. We've got weirs, and we've got, well, these are throttling devices. So this is up in Morpeth, north of Newcastle. And this basically throttles the flow of the River Wansbeck to 100 cumecs to protect the village, or town, sorry, of Morpeth. And it creates a flood storage reservoir upstream. So these assets are important to protect people, to protect property, to protect, well, the way that we live, really. They do come with a cost. The cost from an environmental perspective, of course. The materials that we have to use have to be mined, whether they're steels, whether they're concrete. Of course, when we're manufacturing the products, they produce CO2. There's no ifs or buts, it's what happens. When we're using these assets, for example, land drainage pumping stations and electric gates, we're using electricity, which of course has to be generated from somewhere. Yes, more of it's becoming green, but we need to move more that direction. And then there's the big thing of actually maintaining the assets. People have to drive over to them, which uses fuel at the moment. We use lubricants, which are quite often oil-based, to maintain them. So the maintenance in itself has an environmental impact as well. So I'm going to look at various ways where we can at least reduce it and sometimes completely offset the damage that unfortunately we have by building these assets in the first place. A nice place to start is to look at materials. When we look at materials, quite often we look at, okay, how much CO2 does a ton of, I don't know, stainless steel, cast iron, HDPE, how much CO2 does that use? But we don't always look at the full life cycle. There's been a lot of talk I've heard over the time that, over the last day or two about end of life. Of course, that's also important. Is it HDPE, for example, which can be recycled fairly easily at lower temperatures, or is it steel where we have to really heat it up, which uses a lot of energy to do so? So that's important. Also longevity. How long does the material last? Are you building something for 10 years, 50 years, or 100 years? Of course, if it lasts 100 years and it uses half the CO2 of something that lasts 20 years, you're still better off year on year. But a lot of people seem to oversee weight, or they don't look at it. And the weight is really critical because actually the weight of something is not just the item and the CO2 that comes out of it, but quite often your logistic process. How am I getting this item to site? When it's on site, do I use a crane or can I handball it in? You know, if a crane has to come, or plant or excavator, that's additional diesel and therefore additional CO2. So a nice place to start is with our HDPE flat valves. So traditionally, ever since almost Victorian times, we've been using cast iron for non-return valves. It's big, it's heavy, yeah, it's robust, but it's also not particularly great from a CO2 perspective. We've also got the HDPE, which is what we're moving towards. That does have some question marks about it in terms of microplastics. However, generally, if you impregnate it with carbon, then it's UV stable. Therefore, it doesn't release microplastics in the same way as various other materials such as PVC and whatever else will. This gives you a huge saving on weight. So when you compare, these are all images of 0.5 meter diameter flat valves to give you a fair comparison. The HDPE one, cast iron is middleweight, and stainless steel and carbon is heavy. Stainless steel and carbon is mainly heavy because the design makes it so, because they're always made on a pipe spigot. So they're longer and chunkier, bulkier than what you would have if it was cast iron or HDPE. So what does this look like from a carbon perspective? Well, the HDPE valve for a 0.5 meter weighs only 13 kilos. Therefore, virgin HDPE produces 0.8 kilograms of carbon per ton. So we're only producing 10.4 grams of carbon for a HDPE flat valve. Compare that to cast iron, which is 65 kilos. You're straight away on 8 times more carbon. And you look at stainless steel, because it's 144 kilos, you're up to nearly a full kilogram of carbon for every valve that's being produced. So weight is a big factor. And not just from that, but also a HDPE one at 13 kilos, obviously you can fit that by hand. You don't need any lifting apparatus. As soon as you're looking at 140 kilos, you're looking at plant, which means that you're looking at additional equipment that you requires quite often, which uses fuel. There are other ways, not just about materials, and this is something that ACE really focus on, which is looking at the intelligent design. So we supply Archimedean screw pumps. Our Archimedean screw pumps are unique in the fact that they're fish friendly, but also the full drum rotates and the actual helix within the drum is completely sealed to the outside. That means that we've got no leakage path, so water can't slip between the screw and the trough, which means that everything inside the screw is retained. But the nice thing is, this also means that you can pump into a head of water up to the center line of the shaft. Because you're doing that, it means that your outlet of the pump can be lower than your maximum outlet level. So you can see here, my arrows have moved for some reason, but the outlet of the pumping station would normally is here with our design, when you'd normally have to place it here for a traditional type screw pump. To put this into context, this is Bells and Mockets, which is a site that we delivered for the Environment Agency in collaboration with the Lower Medway Drainage Board. And on this particular site, we managed to reduce the overall height of the asset by 1.25 meters. Now, when you look at an asset which is, 20 odd meters wide, and you're reducing it by 1.25 meters height, that's a huge amount of concrete which we've got rid of. And concrete, as we all know, is a terrible contributor to CO2. The other nice thing is, because the screw doesn't sit in a trough and we can lift it in using these frames, it's self-supporting. So the head walls can come down vertically and run at 90 degrees to the asset. So we don't need the traditional big concrete lump in there or trough which a normal screw pump would sit in, and that they're quite often grouted into place. So we've saved a lot of time on site. We've saved a lot of concrete by going this direction. And this is the overall asset. And then on top of that, it's fish friendly because of the clever leading edge, and there's no pinch points between the vanes and the screw for the fish to get caught on. They've already done some tests, and Hi-Fi are currently, right now, actually doing more DIDSON monitoring on eels on this particular site. We've got to look at upgrading assets. A lot of the environment's assets are quite old. It's possibly an understatement. And by upgrading them, we can find more efficiencies and, yeah, improve the asset from an efficiency perspective in particular, but also get rid of a lot of the traditional, yeah. But anyway, so this is Appledore, which is in Kent. Gives you an idea of where it is. You can see Folkestone down here, Dover. So it's completely in the southeast. Appledore pumping station, this isn't unfortunately a photo of the motor. The motor was already gone when we turned up to go and inspect the site to put forward some ideas. But that is basically the same motor that was being used in that pumping station. This is only 2016, yeah? And we're using something that looks like that. It's a diesel motor, so obviously it's releasing fumes in the environment, but it's also inefficient because diesel motors, you lose energy through heat, but you also lose energy through the mechanical couplings, gearboxes, from the drive shaft all the way through the system. So of course, these kind of technologies, we're way beyond that now. It's 2019, and we should be looking more electric. So Ace installed these electric pumps, which are also fish-friendly technology. So we've got a fish-friendly impeller system on it. 2 canister pumps, each one does 500 litres per second. And just that simple change to electric means that we're already making improvements. We've got rid of the fuel, or the fumes, at least, from the fume. On top of that, there's no gearboxes or anything like that. The motor is direct drive onto the impeller. So you've lost all the mechanical losses are also removed. The other big thing is old diesel technology operates fixed speed. So whatever RPM the motor is set at, it drives a gearbox, which then drives the impeller at that speed, regardless of water level. So your volume is actually changing, which you're pumping, as the water levels are increasing or decreasing. By moving to variable speed, what you end up with is a better curve. So to quickly try and explain pump curves to everyone, this line and this line represents a speed. Yeah, we might call that 500 RPM to keep it easy. This is variable speed, so we've got 3 lines. So this top one represents maybe 500 RPM, this one maybe 400 RPM, and this one maybe 300 RPM. But how we set it up generally, such as at Appledore, is that it's set for a fixed volume. So regardless of how the water levels are changing, the pumps are always kicking out 500 litres per second. If it's fixed speed, it drops off, and what happens is your volume goes up. This is volume across the bottom. So your flow rate increases as your levels draw closer. Problem with that is it also becomes far less efficient because you're moving away from your efficiency points, while here you're staying really at your key efficiency point for the pump. So as you're slowing it down, it becomes more efficient. So to give you an idea, that gives you a direct reduction of power of 25% at that level and 50% when the levels are almost the same. Of course, you are moving more water, so you have to look at it as how many kilowatts per cubic meter am I using? And when you look at it like that, for these 2 pumps, you're saving, at this point, 38%, and the other one 14%. So you're saving vast amounts of energy simply by varying the speed of the pump to match the level differences that are there. So the outcome of that particular project was, no more diesel being consumed. We're using cleaner, greener electricity. Proven and more rigorously monitored fish-friendly impeller. We've got hundreds of reports showing that fish can pass through this thing. Less efficiency loss through the burning of fuel, removing of the mechanical gearboxes, improved efficiency through variable speed, directly driven pump, but also CFD analysis. So it's computational models which we use to develop the pumps, mean that the pumps are much more efficient now than the historic pieces that we saw there earlier. So we estimate an efficiency improvement of that pumping station of at least 30%. It is difficult to pinpoint it because we don't have a lot of the old documents, unfortunately, from the original pump manufacturer. But that's a conservative estimate. They also require less maintenance. Because they require less maintenance, you don't have people driving to and from the pumping station as frequently, which also saves fuel. Let me move on to a new thing, which is carbon neutral pumping stations. Is it possible to make pumping stations carbon neutral? Now, not all of them, but on tidal sites, we've got a huge opportunity to not only pump water out at a low carbon, but actually use gravity in our favor to generate electricity back. So we've developed horizontal pumps. So these are actual flow pumps. So they lie on their side rather than being vertical. By doing that, water can pass all the way through the system, and it's got less pipe friction, so you've got less losses due to your pipe friction that you'd normally have. You don't have losses due to siphoning, so up and over, where you've got to first pump the water all the way to the top of the siphon before it comes back down. So the system is inherently efficient because you've got very little things to stop it being inefficient. The benefit of this is it means that when the tide is low, I'll come back to that because I've got a nice slide to demonstrate it. But yeah, as the water passes through, another benefit is the valves on the outfall of it, you can also lift them up. So this particular site is Schaedam in the Netherlands. And at Schaedam in Holland, they actually sometimes let some saline water back in for environmental purposes. And they do that by lifting the flat valves up into the building. So you can actually send water back as well, which you can't do with a vertical execution. It's not many sites that need it, but for some sites it's definitely interesting. This is the pumping station once it's built, and you straight away see another really nice benefit of this. It's very low. So from a visual perspective and an aesthetic perspective, you don't see that much of it. So if it's in a community or a town where you might worry about what it's going to look like, you're making it as small as you possibly can. These are the pumps when they're being installed. They're quite big, but they do move 7 cubic meters of water each per second. So they are powerful units. And this is where we come to whether we can pump or generate power. So when the outfall level is higher than your inlet, of course you need to pump that water. So you're using electricity to do so. However, when the water on the outfall is lower than your inlet, pumping stations gravitate. And a lot of pumping stations do this anyway through flap valves or sluicing. But actually, if you send the water back through the pump, we can use the pump to generate electricity. This is also partly because of our motor technology that we use in the pump, using permanent magnet motors rather than the traditional induction motors, which are firstly more efficient, but secondly give you this opportunity as well. That means that a lot of pumping stations where you've got a large tidal head, you could potentially make pumping stations completely carbon neutral, as long as, of course, they're only pumping a few weeks a year and they're generating electricity the rest. Now, I want to talk on to something else that's quite exciting, which is biotechnologies for materials that can actually be made completely biodegradable. A partner that we work with already, Janssen Veneboer, we've been representing them in the UK for about 10 years. They make our big lock gates, big stop logs. We're currently delivering some to Dublin, which are 12.5 meters wide and 6 meters high. But they are now also manufacturing using biocomposites. So the biocomposite that we're using for this bridge is made out of flax. So flax is the plant which you use to make linen. So you use these threads get generated from this plant. These threads can then be woven into this kind of material here. So you end up with a completely interwoven fabric. And that fabric can then be layered and set with a biodegradable resin, and you can build bridges out of it. This whole bridge, excluding the support pillars and the metal components and the drive mechanism, that whole section is biodegradable. It's made out of natural materials, mainly flax. Here's a video of it operating. So this is one of the... Ooh, didn't realize there was sound there, sorry. Yeah, so this bridge is... it spans a whole watercourse and it's a pedestrian bridge. So it's the first step. Composite bridges are already being made for road decks, for large bridges. But, of course, you know, you're not going to straight away jump into building a motorway bridge out of biodegradable composites. Try a cycling path first. But it shows where we're going and what might be possible. And that's the end of my presentation. I hope you thought it was interesting, and I'll hand over to you.